great achievement for India, as Aditya L1 shall be the first space-based Indian mission to study the Sun. The Indian Space Research Organisation ready with XPoSat, X-ray Polarimeter Satellite, the country's first dedicated polarimetry mission to study various dynamics of bright astronomical X-ray sources in extreme conditions. The main aim behind the launch of the Aditya L1 satellite is to study the dynamics and space weather of the Sun, making it the first of its kind mission by ISRO. Aditya L1 is named after the Sun's core, and the Indian satellite aims to place itself in a halo orbit around the Lagrange point 1, L1, of the Sun-Earth system, approximately 1.5 million kilometers from Earth. After entering the halo orbit of the Sun-Earth system, the satellite will be able to provide unprecedented insight into the behavior of the Sun. The Aditya L1 satellite will be placed in such a position that it won't be hindered by any eclipse or occultation. The main aim of the Indian space mission to the Sun is to give ISRO scientists the ability to study the activities of the Sun and its impact on the solar system in real time, without any lag or delay. The Aditya L1 has been specially designed to withstand the heat from the Sun. The spacecraft carrying the Aditya L1 satellite near the Sun will be equipped with 7 payloads, each designed to scrutinize various layers of the Sun, from the photosphere and chromosphere to the outermost layer. The XPoSat will carry 2 scientific payloads in a low Earth orbit. There are 2 types of payloads used, namely remote sensing payloads and in situ payloads. Payloads with their major capability of scientific investigation are: Visible Emission Line Coronagraph, VLC, is a remote sensing payloads which is capable of corona imaging and spectroscopy. Solar Ultraviolet Imaging Telescope, SUT, is a remote sensing payloads which is capable of photosphere and chromosphere imaging narrow and broadband. Solar Low Energy X-ray Spectrometer, SOLEXS, is a remote sensing payloads which is capable of soft X-ray spectrometer, sun-star observation. High Energy L1 Orbiting X-ray Spectrometer, HL1OS, is a remote sensing payloads which is capable of hard X-ray spectrometer, sun-star observation. Aditya Solar Wind Particle Experiment, ASPEX, is an in situ payloads which is capable of solar wind particle analyzer protons and heavier ions with directions. Plasma Analyzer Package for Aditya, PAPA, is an in situ payloads which is capable of solar wind particle analyzer electrons and heavier ions with directions. Advanced Triaxial High Resolution Digital Magnetometers is an in situ payloads which is capable of in situ magnetic field. All about X-ray Polarimeter Satellite, XPoSat. The X-ray Polarimeter Satellite, XPoSat, is a ISRO-planned space observatory to study polarization of cosmic X-rays. The telescope is developed by the Indian Space Research Organisation, ISRO, and the Raman Research Institute. Payloads. 2 payloads of XPoSat are hosted on a modified IMS-to-satellite bus. A satellite bus is the main body and structural component of a satellite or spacecraft, in which the payload and all scientific instruments are held. Primary scientific payload is polarimeter instrument in X-rays, POLIX, and XPCT is the secondary payload on XPoSat. Primary scientific payload is polarimeter instrument in X-rays, POLIX, which will study the degree and angle of polarization of bright astronomical X-ray sources in the energy range 8 to 30 kilo-electron volts. POLIX, a 125 kilograms, 276 pounds, instrument, is developed by the Raman Research Institute. Polarimeter instrument in X-rays, POLIX. POLIX is the primary scientific payload aboard XPoSat. It is a Thomson X-ray polarimeter, which measures the degree and angle of polarization, polarimetry parameters, of astronomical sources in the medium X-ray range, 5 to 30 kilo-electron volts. Its objectives are to measure the strength and the distribution of magnetic field in the sources, geometric anisotropies in the sources, their alignment with respect to the line of sight, the nature of the accelerator responsible for energizing the electrons taking part in radiation and scattering. The experiment configuration consists of a collimator, central low Z scatterer surrounded by xenon-filled X-ray proportional counters as X-ray detectors which collects the scattered X-ray photons. Z scatterer consists of lithium, lithium hydride or beryllium. The instrument is rotated along the viewing axis leading to the measurement of the azimuthal distribution of the scattered X-ray photons which gives information on polarization. Polarized X-rays will produce an azimuthal modulation in the count rate as opposed to uniform azimuthal distribution of count rate for unpolarized X-rays. POLIX has 4 independent detectors, each with its own front end and processing electronics. Localization of the X-ray photon in the detectors is carried out by the method of charge division in a set of resistive anode wires connected in series. The prime objects for observation with this instrument are the X-ray bright accretion-powered neutron stars, accreting black holes in different spectral states, rotation-powered pulsars, magnetars, and active galactic nuclei. This instrument bridges an energy gap in detection capability between the soft X-ray polarimeters utilizing Bragg reflection or photoelectron tracks and hard X-ray polarimeters using Compton scattering such as the cadmium-zinc telluride imager on AstroSat. X-ray spectroscopy and timing, XPoSat. XPoSat is the secondary payload on XPoSat. It measures spectroscopic information and timing of soft X-rays. XPoSat is designed to pursue timing studies of soft X-rays, 0.8-15 kilo-electron volts, complementary to what the Large Area X-ray Proportional Counter, LAXPC, does at high energies on AstroSat, while simultaneously providing adequate spectral resolution in the 1 to 20 kilo-electron volts band. It has an energy resolution of less than 200 eV at 5.9 kilo-electron volts and a timing resolution of approximately 2 milliseconds. The detector achieved. The mission will tackle some of the Sun's biggest mysteries. Fresh off its success at the Moon, India is now headed for the Sun. Chandrayaan-3 mission became the first to land softly near the Moon's south pole. Aditya L1's long journey has just begun. This mission will help scientists better understand solar activity, including the dynamics of solar flares and coronal mass ejections. Flares are powerful flashes of high-energy radiation, and coronal mass ejections are huge eruptions of solar plasma. Both types of outburst can affect us here on Earth. Intense coronal mass ejections that hit our planet, for example, trigger geomagnetic storms that can disrupt satellite navigation and power grids. Aditya L1 will also tackle the coronal heating problem, one of the biggest mysteries in heliophysics. Aditya L1 will measure the composition of the solar wind and attempt to determine how it is accelerated.